so now we're going to think about multiple correlation in R squared. And so that is really the multiple regression extension of correlation and R squared. So the multiple correlation is the correlation between the observed Y values, so this is the actual response, and the predicted Y hat values. So this is what the equation predicts based on the model. The multiple correlation is denoted by capital R. In simple regression, the correlation coefficient is little r or lowercase r. The multiple correlation is capital R, and it is something different. In simple regression, the correlation is the correlation between the response and the explanatory variable. In multiple regression, the multiple correlation is the correlation between the observed Y and the predicted Y hat. So it is a very different kind of idea. The multiple correlation summarizes the relationship, or the strength of the relationship, between the response Y and all predictors as a set. So it's looking at this regression relationship, the response Y, say blood pressure, and the set of predictors age and weight together. So how good are age and weight together at predicting Y, or how strong is that total relationship between age and weight together and the response blood pressure? So it's not looking at blood pressure and just age. That would be the correlation lowercase r. And it's not looking at blood pressure and weight. That would be the correlation lowercase r between blood pressure and weight. Instead, the multiple correlation is looking at blood pressure, the overall response, and the set age and weight together. And to do that, it's looking at the predicted response because that is based on age and weight together. Now, the multiple R squared is like the multiple correlation squared. And it's found the exact same way as R squared was in simple regression. It looks at the total variability in Y, or SS total, and it subtracts off the variability around the regression equation, or SSE. So here we have the variability around the grand mean, Y bar, and it looks at the observations around it. And then for SSE, this is really looking at the errors around our prediction equation. So how big are the errors or our residuals? And it compares them. So for residuals around the prediction equation are about the same size as the variability around the grand mean, that flat line, then our R squared is going to be pretty small. However, if the variability around our prediction equation is very small relative to the variability around that grand mean, then our prediction equation is doing a good job, and our R squared is going to be large. So let's look at our BP data, our blood pressure data that we've looked at before. Here we have our actual response, so this is our Y. And along here, along our x-axis, our horizontal axis, we have Y hat. So this is giving us an idea about the relationship between Y and Y hat. This is giving us a sense of the strength of association between our observed values and the predicted Y hat values. So all of these points in here are our observed and our Y hats. The strength of association between these observed and Y hat values is the multiple correlation. And we see here that there is a very strong positive linear association between the observed Y values and the Y hats. So the multiple correlation is very strong. And that makes sense. If we look at the R squared here, the R squared is 0.99. The square root of 0.99 is also very large. And that would be our multiple correlation. So if we were to take our predicted responses and our actual responses and plot them against each other, the strength of the association between those, which is what we have here, that is our multiple correlation. So let's interpret this R squared for the blood pressure data. R squared here is 0.99. That means we explain 99% of the variability in blood pressure by using age and weight as predictors. That's nearly all of the variability, and that makes sense because almost all of these points, almost all of our actual values are on this line. This is not our prediction equation, but we can see that there's basically no variability left over. Our predicted values are almost exactly the same as our actual values. There's almost no difference between our observed and predicted values, so there's almost no variability or error left over. So let's think about this a different way. If y hat, if my predicted values are exactly equal to the grand mean, so if my y hats, my predicted values for my regression equation, are exactly equal to this y bar, that flat line, then my R squared is going to be 0. My regression equation is useless. That means I basically have a flat line. I'm not doing much. If my observed value equals y hat, so if my observed value equals y hat for all observations, then my R squared is going to equal 1. There is no leftover variability. That would be perfect prediction. We almost have that here with our blood pressure data. Here, my observed values are almost exactly equal to my predicted values, but not quite. So let's think about how R squared changes when I have different models. On the left-hand side, this is all going to be simple linear regression models. On the right-hand side, we're going to see what happens when I build up multiple regression models, but adding one variable at a time. Now, this is not the way we would typically build a multiple regression model. If we think that our explanatory variables are useful, we should add them all to the model, because otherwise what are we doing? So the only reason I am going to be building it this way, this is just for illustration purposes. This is just to illustrate what happens to R squared. This is not how to build a model. I cannot stress this enough. This is just to show what happens to R squared. This is not the way to build a model. If you believe your explanatory variables are useful, you should include them in the model. All right, so this is with the candy bars data set that are already uploaded on ELC, and we're going to start with the left-hand side. On the left-hand side, as I said, we're going to build a bunch of simple regression models, and we're going to see what the correlation squared, which is the R squared for each of those models. So we're going to predict the calorie content once using fat, another time using just sugars, a third time using just protein, and then a fourth time using just the dietary fibers. So the candy bars data set, as you'll remember, has a whole bunch of possible variables, and we're going to look at these 4. So I'm going to do analyze fit y by x because I'm doing a bunch of simple regression models. And I'm going to put calories in my y box, and I'm going to have fat as an explanatory variable. And because this is a fit y by x situation, as whatever I put in this x box here is going to be treated as a separate simple regression variable. So I'm going to get a separate analysis. So I also want to include sugar, and then I have protein, and then I have fiber. So whatever I put in this x box, I am not going to be building a multiple regression model because I'm doing fit y by x. I'm going to have a separate simple regression relationship for each of these. I'll show you what that looks like. So now I have 1, 2, 3, 4 separate scatter plots instead of one overall model. So if I want to know about the simple regression relationship between calories and fat, I can do a fit line. And this is only telling me about the relationship between calories and fat. It's not including sugars, fat, and sugars, protein, and dietary fiber because I did not use the correct dialog box to do a multiple regression relationship. But that's okay because I'm only interested in the simple relationship between calories and fat. What's more, I just want the R squared value for calories and fat, and that would be this value, 0.65. So I'm going to put that in my notes. The R squared for calories versus fat is 0.65. I'm going to do the same thing for the relationship for sugars, protein, and dietary fiber. So I'm going to fit the line for the relationship for calories and sugar. And for the calories versus sugar, I get an R squared of 0.17. For calories versus protein, I get an R squared of 0.31. And finally, for dietary fiber, coming all the way over here to the right, I get an R squared of 0.22. So before we go any further, let's interpret what each of these means. When I use fat as a predictor of calorie content of candy bars, I explain 65% of the total variability in calories. Or fat explains 65% of the total variability in calories in candy bars. On the other hand, sugars only explains 17% of the total variability in candy bars. Protein explains 31% of the total variability in candy bars. And dietary fiber on its own explains 22% of the variability in candy bars. Now, because these are simple regression models, this is just the individual explanations. So this is what fat does on its own. This is how sugar does on its own. This is protein's unique explanation, and this is fiber's unique explanation. It is not holding any of the other variables constant because this is just simple regression. Now, if I want to think about multiple regression, I come over to the right-hand side, and I'm going to build each of these models in turn. So, the first thing I'm going to do is build a model that uses just fat to predict calories. Well, when I use just fat to predict calories, I'm going to have an R squared of 0.65, because that's the simple regression equation. So, we already know that fat explains 65% of the total variability in calories. Now, the question is, when I use fat and sugars together, how much the variability in calories is explained? To answer that, I need to build a multiple regression model. What do you predict is going to happen? Is this R squared, am I going to explain the same amount of variability, more variability, or less variability when I have both fat and sugars in the model? Well, let's do it. I have to go to Analyze Fit Model to get a multiple regression model. Calories is my response variable, and now I want to include both fat and sugars as my explanatory variables. The Analyze Fit Model dialog box is different than the Fit Y by X because now I'm including multiple variables that I want to understand their effect on the response. So Y is still my response, so calories goes in Y, and now I'm looking at both fat and sugars and their collective effect on calories. And I hit run. We can see I've got different output because it's a different model. But what I'm interested in now is this R squared. That's the only thing we care about for this lesson. So the R squared, when I have both fat and sugars predicting calories, is 0.82. Is that what you predicted? Did you predict that the R squared would go up from 0.65 to 8.82? Did you predict that it would go up but not by as much? Did you predict that it would go up but by more? Did you predict that it would stay the same? Well, I hope that you predicted that it would go up because we saw that sugar did explain some of the variability in calories. In fact, it was able to go up by as much because sugar and fat are not really that related. Fat is kind of its own thing, and sugars is kind of its own thing. But sugars are not fats, and fats are not sugars. So the qualities in calories, or the calories that are related to fat in candy bars, are not the same calories that are related to sugars in candy bars. So you can just pour more and more and more sugar into a candy, and that's not going to change the fat content. And you can also pour more and more and more fat into a candy bar, and that's not going to change the sugar content. But both of those things are going to increase the calorie content. And we can look at that relationship by looking at a scatter plot matrix. To get a scatter plot matrix in JUMP, we will go to Analyze, Multivariate Methods, Multivariate. And this allows us to plot a bunch of variables at the same time. So I'm going to plot calories, fat, and sugars in a scatter plot together. I'm going to remove these ellipses because they kind of obscure things, and I just want to look at this plot. I see here that as fat increases, the calories also tends to increase. So I'm looking at the overall relationship of this first plot. On the top row. So as fat increases, calories tends to increase, but we've already seen that. And I also see a general, in the top plot on the right, a general positive linear association between calories and sugars, but it's a lot weaker. We do see that as sugars increases, calories increases, but it's not as strong an association. And that makes sense because the R squared, which tells us about the amount of variability that sugars explains in calories, is lower. And then let's look at this next column down, or this next, the plot below that of calories and sugars. So if we look at the plot explaining fat and sugars, so it's the plot in the middle row all the way to the right. We see that as sugars increases, fat doesn't really seem to do anything. There's not really an association between fat and sugars at all. And that kind of makes sense. That's like saying that I can dump more sugar into a candy bar and that's not going to change the fat, and I can dump more fat into a candy bar and that's not going to change the sugar content. And that's really what we see here, that there's not really any association, linear or otherwise, between fat and sugars. And if that's true, then we can say that fat and sugars are basically independent. They may not be perfectly independent, but there's not any real association. So the explanation of variability that sugars brings to the equation is different from that fat does. They're unique contributions to the R squared. Now, let's go back to our notes. We saw a pretty big jump, a kind of maybe surprising jump when we added sugars to the explanation. Sugar itself, on its own, explains the least amount of variability, but we still got a big jump when we added it to our equation. Now if we think about our simple regression equation, we saw fat explains 65% of the total variability, sugars explained the least, but it got us a big jump. And now we see protein. Protein explains the second most amount of variability, explained 13% of the variability on its own when used as a predictor of calorie content. What do you think is going to happen? What do you predict will be the change in R squared when we add it to a model that already has fat and sugars in it? Do you think that we're going to have an increase in R squared, a decrease in R squared, or do you think that R squared is going to stay the same? That is, think about what R squared tells us, and what do you think is going to happen to it when we add protein to the model that has fat and sugars in it? Okay, so let's go back to JUMP and actually fit this model. I'm going to go to Analyze, Fit Model, and I'm going to predict calories using fat, sugars, and protein. I'm going to hit Run. I see a lot of output that I don't need, but I'm going to scroll down, and I see that the R squared is 0.85. When I use fat, sugars, and protein to predict the calorie content of candy bars, I explain 85% of the total variability of calories. So my R squared here is now 0.85. Is that what you predicted? Did you predict that the R squared would go up? Did you predict that it would only go up by about 3 percentage points? Why does it make sense that the R squared would go up a lot when we added sugars to a model that only had fat, but would only go up a little when we added protein to a model that only had fat, that already had fat and sugars? Well, remember, we said that when we add sugar to a candy bar, it's not really telling us anything about fat. And when we add fat to a candy bar, it's not really telling us anything about sugars. But think about protein and candy bars specifically. Where does protein come from in a candy bar? Protein technically comes from anything that is organic. Protein is a building block of life. But in candy bars, we see protein in things like butter and caramel, and more specifically, peanut butter and peanuts. But we also know that peanut butter and peanuts are have high concentrations of fat. And so if we're adding more protein to candy bars, we're probably also adding more fat to candy bars. So if we're already explaining a lot of the calorie content with fat, then protein may also explain some different unique things about calorie content, but not that much. Maybe it'll explain some unique things because of caramel or butter that isn't already captured by that fat variable, but there's a lot of overlap between what protein and fat do. We talked about this when we were thinking about protein as a lurking variable. Let's look at that plot again. I'm going to pull up a scatter plot matrix of protein, fat, sugar, and calories. So we go to multivariate methods, and I said we're going to look at calories, fat, sugars, and protein. I'm going to hide these ellipses because, again, I think they're a little confusing. And if we look at this first plot, if we look at this plot of calories versus fat, we can see that strong positive linear association. And we can see that weak positive linear association between calories and sugars. And we can see that moderate positive linear association between calories and protein. Fat and sugars are unassociated, but fat and protein have a fairly strong, at least a moderate positive linear association. And so if we're thinking about the variability explained, fat's already doing most of it. And because of that relationship between fat and protein, when we then add protein to the model, there may be a relationship between calories and calories and protein, but in terms of what's left over for protein to tell us about calories, there's just not that much. So, because of that relationship between fat and protein, there may be a relationship, but there's not unusual information or unique information for protein to tell us about calories. And that's why the R-squared didn't go up that much. Fat was already doing all that heavy lifting. Now let's think about one more variable. Let's think about fat, sugars, protein, and dietary fiber. If we add dietary fiber to this model that already has fat, sugars, and protein, what do you think is going to happen to this R-squared? It's going to go up, down, or stay the same? Well, let's fit this model. I'm going to fit this model using Analyze Fit Model, and I have calories as my response, and now I'm going to include fat, sugars, protein, and dietary fiber as my explanatory variables. And if we scroll down just looking for that R-squared, we see that the R-squared is now 0.858. Before it was 0.854. So we'll give them the benefit and we'll round up to 0.86, but it has hardly gone up. It has gone up by less than half of a percentage point. Is this what you predicted based on the R-squared from the simple regression equation for dietary fiber and calories? Why do you think that dietary fiber has contributed so little to this R-squared? Do you think maybe for similar reasons as we saw for the protein contribution? What is the best model? Do you think that we should include all 4 of these variables? Do you think maybe we should only include 2 or 3 of these variables? If we were using R-squared as a determinant for a model selection for which best model we should use, how would you decide? I probably would not choose this model because the difference of 1 percentage point between 0.85 and 0.86 in terms of R-squared isn't that much. That's not that big of an effect. I can do basically just as well using 3 variables as I could with 4. So the complexity introduced by having a 4th variable, dietary fiber, to my model for the gain of barely 1 percentage point in R-squared isn't worth it. We're always trying to balance in statistics this idea of complexity against explanatory power. So yeah, I've got more explanatory power with an R-squared of 0.86, but not much. And I now have a more complex model. If I have to think about how to interpret these parameter estimates, these slopes, I have a much more complex parameter space. I'm now in a 5-dimensional space, and I now have to think about what it means to hold fat and sugars and protein constant to interpret that slope for dietary fiber. Not worth it. So I might want to choose this model that has 3 explanatory variables. But then I might say, is the difference between 3 percentage points worth it? Is that a big enough or meaningful effect? Is explaining 85% of the total variability worth it for this more complex model, when I've also looked and seen that protein and fat have a sizable correlation? Fat is already explaining much of what protein does. Maybe I want to just focus on this simple model and not worry about those 3 extra percentage points in variability. 82% is still a pretty high amount of variability explained. And I can picture, I have the benefit of being able to visualize a 3-dimensional model if I only have 2 explanatory variables. In the end, because I have a lot of experience, would probably come down to this model. It also would probably help if we looked at our parameter estimates and tried to interpret the size of the effects as well to help us make these decisions. We can also look at the p-values and use that and inference to help us make decisions between model comparisons. But this is something we might want to consider, right? So R-squared, though, will never decrease when we add explanatory variables. So we can't say, well, we have this really high R-squared, therefore the model is useful, right? It will always go up. We can add, the number of workers on the assembly line, and that will tell us, that will be in some ways a useful predictor in terms of the number of calories, just because we had so many other variables already in the model, right? So be mindful of the size of your model when interpreting your R-squared. Worst case, R-squared will stay the same or approximately the same.